Welcome everybody, and thank you for attending this other seminar in the PQ Cifris initiative. This indeed is the December seminar of this PQ Cifris initiative, which is, as you know, a thematic group within the Italian Cryptologic Research Association, the componendis Cifris. Today we have the pleasure to host a talk by Cecilia Boschini, who currently is a postdoc researcher at Technion and Reichmann universities. She got a PhD from Università della Svizzera Italiana in Lugano and also worked at IBM research laboratories in Zurich. Her research basically concerns post-quantum cryptography, which is the theme of our group indeed, and lattice-based crypto in particular, with focus on privacy-preserving signature schemes and policy-enforcing encryption protocols. Today, Cecilia will give a talk on the information leakage that may occur during the verification stage of some signature schemes. It's enough for me. Thank you all again for attending. Please do not hesitate to put questions if you wish. Possibly at the end of the talk, we will have some time for discussion, but also during the talk if you need. So, Cecilia, thank you again. The floor is yours.
Thank you very much. Hi all. I'm very happy to be speaking at this seminar, and I'm really thankful that I got this opportunity. Thank you, Max and Marco, for inviting me. And I'm going to talk today about a result that coincidentally is an all Italian result, because it's essentially part of the major part of this talk is going to be, it's taken from a joint work with Fiore, which is at IMDA Research in Madrid, and Elena Pagnin, which is at Lund University in Sweden. And it's, as Marco already said, is related to what happens when we want to do efficient verification on an existing digital signature. So to start, let's just let's say summarize real quick what a digital signature is. A digital signature is a triplet of protocols, of algorithms actually. A key generation signature is signing and verification algorithm, and it's in between two parties, a signer, which here is Alice, and a verifier, which here is the Mad Hatter. And works as the dynamic is as follows. First, Alice generates a signing key and a verification key, and then the signing key stays secret, obviously, and the verification key is published for all the verifiers to use. And then when it's time to sign a message, Alice will use her secret key to produce some bit string sigma, and then we'll send the message and the bit string sigma to the verifier. At that point, the verifier will take this pair and compare it somehow using the verification key to make sure that there is some relation between sigma, the message, and the verification key. And the verification algorithm will output 0 if there is no such relation. So if the signature was not output by Alice, and it outputs 1 in the other case, if the signature is valid. Obviously, we would need some security guarantees, and they're actually quite trivial. What we would like to have is that if an evil verifier, a corrupted verifier that sees many pairs message signatures, well, we would like for this verifier not to be able to actually forge a signature. So whatever pair message signature message star, sigma star that the adversary is going to come up with will not pass verification. Will always the verification on this pair will always return 0. Now, what happens in practice is that some signatures are either require a lot of time to verify, or the verifiers need to verify many signatures at the same time. So what happens is that in implementation, maybe one would come up, instead of using the verification, the normal verification algorithm of a scheme, one would rather use something more efficient, what one will call an efficient verification scheme. And such a scheme, such an algorithm, sorry, would be faster, so require less computation than the verification algorithm. But because of this, it's not really sure whether we still have unforgeability. I mean, if we're doing less checks than necessary, can we still guarantee that a corrupted verifier cannot impersonate Alice? And this is actually a problem in practice, because what we would like is that if something is rejected by the normal verification, it's also rejected by the efficient verification, in the sense that the efficient verification can still detect forgeries attempt. But what happens in practice is that actually this is that's what the case we're interested in practice is the case where this doesn't happen, where the efficient verification is doing so little checks that sometimes there could be some forgeries that are undetected. So we would like now to give a framework to avoid this. And the whole idea of this particular framework is coming up because when it comes to quantum safe signatures, these kind of algorithms are required and quite easy to implement. So it's important to know how to analyze them. And to see this, throughout this talk, we're gonna see a use case for a particular style of post-quantum signature, which is the signatures that have a verification algorithm that works in two steps. There is a first step, which is sum check, and a second step, which is a matrix vector multiplication. Now, the idea is that in these kind of signatures, the public key is a pair, and it's a pair of a matrix A and a vector V. And for example, one can imagine then the vector V could be the hash of the message. And then a signature would at this point be a somewhat short vector sigma, such that A times sigma is equal to the hash of the message. And this is actually, can vary a bit depending on the signature. Not all signatures have a vector V, which is actually the hash of the message. But for the sake of this talk, we're going to consider always A as being a fixed public matrix, and V as the hash of the message that Alice has signed. So signatures of this kind can be constructed from lattice-based assumption or from multivariate equation-based assumption. And now let's assume that we have a constrained verifier. So a verifier that cannot really do all this computation. What one could think of doing is not to check all the row, all the multiplication between the rows of A and the signature, but just select a bunch of them at random. For example, in this example, it's 3 of them, the first, the third, and the sixth, and check that the product of these rows of A with sigma is equal to the right entry of B. And again, on top of this, to check that the norm of sigma is small, but for the sake of this talk and in general, checking that the norm is small is quite easy. The computationally heavy part is always to check that this matrix vector multiplication. And now bear in mind that these matrices and vector are over the Q, so have bounded coefficients. So we have parameters to estimate how computationally heavy this is. That being said, let's go back to what we were saying. So let's assume that we want to check k random rows of A instead of checking the product of the whole A times sigma. Is this actually secure? Well, the gut feeling is not great, because there is quite an easy, one could find quite an easy attack. For example, let's assume that the verifier only checks one row, and given that n, the number of rows of A, is polynomial, what the adversary could do is to guess which row the verifier is going to check. For example, let's guess it's the first one, and then the adversary could set all the components of sigma to be some random values. The important thing is that they're small, so from sigma 1 to sigma, all of these sigma 2 to sigma M, they can be set just at random. And then the last one, the sigma 1, that can be set to be can be extracted from the equation A1 times sigma equal to V1, where V1 is the first component again of the hash of the message. So it's computable. Even more so, we need to assume that Q is prime, so that we're sure that we have the inverse to compute sigma 1. And then the only issue that, so this new vector that the adversary would come up with, of course, is not a valid signature if one tries to verify it with the normal verification. So with the product A times sigma equals, if one checks the whole product, A times sigma equals bool. However, it's going to pass the efficient verification. And the only caveat could be the check on the norm. But if the adversary chooses small enough component sigma I, even if sigma 1 is quite large, the overall norm, for example, the Euclidean norm, is going to be small enough depending on the component, on the computational assumption underneath the scheme. But in general, this attack could actually work. So this idea of just checking random rows of A is not a good idea. We need something smarter, and something better could be the following. Instead of checking k random rows of A, we could check whether the product of sigma with the k random linear combination of rows of A is actually has actually a specific value. And the idea here is that we can sample a randomly chosen matrix C that has less rows, and then compute C times A, and then C times V, and then clearly if A times sigma is equal to V, then also C times A times sigma is going to be equal to CV. Now you could say, well, this is actually a stupid idea, because now we're doing even more computation than what the verification would require, as we're doing a matrix C times A. And even if C is small enough, it's still on, like, it doesn't look like it's a reasonable way of doing efficient computation, efficient verification. And I would tend to agree. So we have actually two things that we need to check. First of all, if this is secure, and second of all, can we reuse the random matrix C? Because we're going to see that actually on the long run, if we reuse the same C to verify many signatures, actually we have a gain in efficiency. However, reusing C actually implies that, as we saw already before, the verifier now has a secret key, which is the matrix C. And we need to make sure that whenever the verifier actually outputs something, so verifies the signature, there is no leakage of any information related to C. And this is going to be, we will see that this is essentially the core part of analyzing these kind of signatures. And this is the leakage that you also saw in the title. Right, so in the paper with Dario and Elena, we had a bunch of results. In particular, we had a model, a formal model to treat these kind of signatures with efficient verification. And then we analyzed these signatures, this kind of post-quantum signatures, giving a compiler for them and proving concrete security. And by concrete security, we mean that security will depend, obviously, in the number of queries that the adversary can, in the number of verification queries that the adversary can make. And this is because, by definition, the efficient verification does not guarantee, give the same security guarantee as the normal verification. And we'll talk about that a little bit afterwards, at the very beginning of the main part. And then we have an analysis of the leakage. And then we can also expand this model. This we will not see in the talk, but it's in the paper. We can expand this model to consider even cases in which the verifier is efficient and then is interrupted in medias res. So instead of doing all the computations, it actually stops at a certain point. And then one can see, one can show that the verifier can actually extract information depending how many computations it has done. All right, so in this talk, I plan to do the following: to show the formal model of efficient verification, which is quite straightforward and easy, and then to show the application to post-quantum signature, so essentially analyzing the intuition that about efficient verification of post-quantum signatures that I've given before. And then in the very last 5 minutes, I'm going to go a bit deeper and talk about more technical and quite interesting future direction in efficient verification of signatures. And while I'm pretty sure that the core part of the talk is going to be easy to follow, maybe this last part might be a bit hard, but I promise that if there is time, this is going to last only 5 minutes. So if that part is hard to understand, that's normal, and it's not going to last long, worst case. All right, so let's start with the framework. And so we define signature scheme augmented with efficient verification as a core signature scheme, which you can see here is the sigma, to which we add the extra algorithm to do efficient verification, which by definition, as we said already, it has to be more efficient than doing the normal verification, but it's going to guarantee lower security. And the reason for this is that if you can find a verification scheme, a verification algorithm that is much faster than the original verification and gives exactly the same security guarantee, then you just have a better version of the signature scheme. There is no need for a new model and no need for further analysis beyond whether the new signature scheme with this new verification algorithm is secure. So in details, we're going to define the efficient verification as a pair of algorithms. It's not always going to be like that, but as we've seen already, there might be secret information that the efficient verifier might want to pre-compute and then use to do verification. So for this reason, we define efficient verification as a pair of algorithms. One is the offline verification, where once the efficient verifier receives the verification key, will make some computation, pre-compute some stuff. And then with the online verification, it will be the actual efficient verification procedure where the verifier will take in a signature and check whether it's a valid signature or not. And so in particular, we have two new parameters here: the secret verification key, which could be just so in the other example would have been the random matrix C, and in general, it's some pre-computed information that can be used to speed up the verification. And a confidence level K, which is essentially a number that, depending on the constraint of the verifier, is going to bound the number of computation that the verifier wants to do. For some definition of bound of number of computation, depending on the adversary. Right. Now we need to give the normal. Now we need to give the normal definition of correctness, efficiency, and security, which are quite straightforward. Correctness just means that whatever is valid for and is accepted by the verification, it has to be accepted by the online verification, the efficient verification. And this is obvious because there is no point in having a better algorithm that's going to reject valid signatures. If we want a better algorithm that is always accept the valid signatures, and now we only need to check that there are no acceptance of not valid signatures. So this is correctness. And then for efficiency, as we said, it might not make sense to have a secret verification key if you need to refresh it all the time. I mean, one could think, okay, I can split the verification into two parts. One happens offline and one happens online. And maybe I can run the offline algorithm at night and then the online algorithm during the day. But this doesn't really help when it comes to evaluate whether the algorithm is more efficient. We would like to reuse the C, and in particular, we would like to make sure, to reuse the secret verification key. In particular, we would like to make sure that if you run the offline verification only once and the online verification are timed, then the cost of doing this, the computational cost of doing this, is actually much smaller than the computational cost of just doing our normal verification. So that's why we talk about concrete amortized efficiency. And finally, we need to define security. So the security is, as per usual in cryptography, proven through a security experiment where we have an adversary, which is here the Cheshire cat, which has the verification key and access to some oracles. In particular, the adversary has access to a signing oracle. So an oracle that on input the message, which you can see here, returns a signature. But also in this case, as the secret key is not one, but there are two of them, there is also the verification key. The adversary also has a second oracle, which is a verification oracle, where on input the message, a pair message signature, the verification oracle will output the outcome of the efficient verification of such a pair. And then the rest is the same. We define a forgery if an adversary can come up with a pair message signature that does not break the original signature, so it's always rejected by verification, but it is accepted by the online verification. And the reason why we are considering the case in which the forged message signature is already rejected by the original signature scheme is because we are obviously assuming that we're optimizing a signature that has been proven secure. So there is, like, forging a signature for the original scheme is not going to happen. The only thing that could happen is that the new verification scheme is not thorough as the original one. All right, so the model is quite easy, and I'm going to guess that there are no questions about this. So I'm going to move on and show you how to use it, because now what we will need to do, once we're going to go back to the signature, the kind of signature schemes that we saw in the introduction, and we're going to try to prove whether the intuition of using this random matrix C for the verification is actually yields a secure signature with efficient verification. And the security proof is going to be essentially made of two steps. The main one is the easy one. So we need to understand whether it's actually easier to come up with a forgery that is accepted by the online verification instead of the verification. And the second step is going to be the leakage part. Because we added a new secret key and a new oracle, we need to make sure that the new oracle actually doesn't leak information about the new secret verification key. Otherwise, the adversary could exploit this to find a forgery. All right, so let's go back to our signatures. And in particular, we're going to consider, as we mentioned already, this Hessian sign signature. So a signature now is going to be, again, a short vector sigma, such that the public matrix A times sigma is equal to the hash of the message, which we called proof before. And security, so this signature, this is a signature that is constructed from lattice-based hardness assumptions. It's a very standard one, it's quite old actually. And it's not exactly what has been, what is in the process of standardization by the NIST. But towards the very end of this talk, I'm going to mention the ones that are actually in the process of standardization, and I will, in the very last part, I will briefly touch on them and see what can be done on that part. But for the sake of this talk, we're going to use this, which is much easier to understand. And the intuition of the unforgeability of this signature is that solving the linear system A times sigma is equal to B for fixed A and B is usually easy because you can do it with Gaussian elimination. And A has more columns than rows, so it's easy to do. However, the problem becomes hard if you have a constraint on the norm of the solution. So if the solution has to be small, only in a particular subset, then all of a sudden finding such sigma is not that easy. So that's essentially why the signature is unforgeable, because the only way to find it if you know some secret information regarding how you built A. This is called a trapdoor, and this is how one could sign. One would generate A with this secret information, and then it can produce these short vectors. But without that secret information, solving this kind of systems is hard with the bound on the norm. Now, what happens if we have the efficient? Well, so as we are considering these signatures where the vector V is actually computed from the message, we cannot pre-compute anything related to V, because V is going to change with every message signature pair. However, we can compute C times A offline. So what you can see on the right, and what we had also before, is just the compiler for just a description of how the efficient verification algorithm would work. You don't really need to have a look at it. The only thing that you need to know is that when what you're going to do offline is you sample a random matrix C in the Q K times N, and in such a way that C has rank K. And the reason for it is that otherwise, I mean, if C doesn't have maximum rank, there is no point in using in checking linearly dependent rows of A. That being said, so you sample C, you multiply it times A, and then you store it. And when it's time to sign signatures, to verify signatures, you will just hash the message, compute C times V, which is a much shorter computation than what you had to do before, and then compute C times A times sigma is equal to C times V, where C times A you already stored. So you compute that part. And of course, you will need to do the norm check. The norm you always need to check separately, but again, this is usually not that hard. Right, so is this secure? And the answer is yes, but requires a couple of surprising steps. In particular, let's go back to our unforgeability experiment. Well, a forgery against this scheme, it can be of two types. Either you forge a signature that was not produced by the signer, but is accepted by verification, or you produce a signature that was not produced by the signer and would be rejected by the original verification, but is accepted by the efficient verification. So the first one, as we saw already, is impossible, because we're assuming that the original signature scheme is secure. The second one is the one we're interested in, and we're going to call this event the bad event. And so the definition of the bad event is, you can find it on the slide, and essentially it says if at any point in time in the game the adversary submits the message either to the oracle or at the very end of the game to the two verifiers that is not accepted by the verification, but it is accepted by the online verification, then the adversary wins. This is the event we want to prevent from happening. And the event could happen at any time during the first QV queries by the adversary to the oracle, or at the query QV plus 1, where by QV plus by this query we mean when the adversary outputs the final forgery, the one that's in the game you can see written in red. Right, so at this point, we can, I mean, it's easy to see that this is in fact, the probability of this event is less or equal than the sum of the probability that this happens at each query during the game. So it's the probability that it happens at the first verification query plus, or it's less or equal than the probability that it happens at the first verification query plus the probability that it happens at for the first time at the second, so not in the first, but in the second, etc., all the way to the probability that the adversary outputs the bad forgery at the very end of the game. And this probability is where we can actually see the leakage, because what these events, the probability that the forgery happens at the query E, given that it did not happen before, this depends on how much gets leaked in the previous verification queries. So this probability is going to increase with the amount of information that the adversary can extract for every query. And we're going to show that this probability, in fact, obviously depends on K, the amount of computation that the verifier did, and it's less or equal to of 1 over q to the k minus I minus 1, which then it's easy to see that this that we get the bound that we saw at the beginning, so qv plus 1 over q to the k minus qv. And again, qv is the number of queries, of verification queries, q is the modulus that we're working with, and k in this case is the number of random linear combinations of row of base that the efficient verifier is willing to check. All right, so the leakage. Now, analyzing the leakage, it's not too bad, not hard, but also surprising, because the leakage happens in a very specific case. So let's now focus on the interaction between the adversary and the verification oracle. So the adversary will send a pair of message signature, and then it's going to receive the answer of the online verification run on them. So what the adversary knows is, given a pair of message signatures, is the value of W. So the value of A times sigma minus the hash of the message. And W, of course, is 0 if sigma is a valid signature. But if sigma is not a valid signature, then W could have any non-zero value. So, and this value is known by the adversary because A is the public key and it is the public verification key, and B is just the hash of the message which the adversary knows. And the leakage happens if, from the knowledge of W and the outcome of the oracle, the adversary can extract information about C. And the outcome of the oracle can be, mathematically speaking, is actually the product C times, whether the product C times W is 0 or not. Because if this is 0, then you're going to have an accept. If this is non-zero, then the efficient verification is going to reject. So in the table at the very bottom left of this slide, you can see all the possible cases. The verification oracle is going to accept if the online verification accepts, but then we don't know what the verification could either accept or reject. And the same in the rejection case. Now let's analyze the four cases separately. So the first one, if the adversary submits a signature that would have been accepted by the verification, and it's also, this signature is automatically also accepted by the efficient verification. Because if sigma is accepted, it means that W, so A times sigma minus V, is actually equal to 0, which means that C times W is clearly also equal to 0. Now, in the case in which the online verification rejects something that the verification accepts, this can actually not happen by definition, because in this case, it means that a valid signature, so something accepted by the verification, was rejected by the efficient verification, which is what we didn't want by policy. So this case is never going to happen. Now, the case in which the online verification accepts and what the verification would reject, so a not valid signature, well, this is exactly the forgery we're interested in. So in this case, there is no leakage, the adversary wins the game. So the only case that can happen, and where there can be leakage, but there is no forgery, is the rejection case, which is a very surprising one. So what happens is that if the adversary is going to submit a signature that is not valid, and the adversary knows that it's not valid, if it's also not accepted by the online verification, in which case would be a bad forgery, then the adversary can extract information about C. In particular, the fact that the signature is not accepted by the verification means that the vector W up here is actually not 0. And if it's not accepted by the online verification, it means that C times W is actually not 0. So what this means is that the adversary now knows that the rows of the secret matrix C are not in the left kernel of the vector W. And this is quite important because what the adversary could do is just come up with random signatures that obviously will not verify because the adversary doesn't know, it cannot forge valid signatures, and then submit them to the verification oracle and starts assuming, okay, starts, let's say, removing from the set of all possible matrix C all these hyperplanes that are identified by the W. So, and this is proper leakage, and we need to understand how much it is and whether it could lead to a forgery. So, this is going to be the last step of the proof, of the security proof. So before the querying phase, the only thing that the adversary knows about the secret verification key is that it's a matrix, means that Q to the K times M of maximum rank. So it knows the cardinality of this set, which is extremely large, and guessing C, though, is not possible. Now, after I verification queries, the adversary has started removing from this set C all the hyperplanes identified by the various W's. So the A times sigma J minus Bj, where Bj, again, I remind you, is the hash of the message. And then if you can see this with some easy computation, then the probability that the adversary eventually has a forgery at the ETH query, it's less or equal than the probability that the adversary can the probability, sorry, that the randomly chosen C is actually in the hyperplane generated by the Wi over the probability of choosing a C at random, and that this C is not in the set of the possible Cs at that point. And this is, so these probabilities you can compute, and essentially you can see it's the cardinality of one of the hyperplanes over the cardinality of the set of the possible Cs at the ETH query. And this, again, you can compute these cardinalities, you can compute with the normal combinatorics, and what you're going to get is that with every query, the set of possible Cs shrinks by a factor that is essentially Q to the K minus the number of the queries. And by plugging that into our formula, we get exactly the probability that we saw already at the beginning of the presentation. Right, and with this, essentially, we're done, because as we saw before, over here, once we can estimate the probability that the forgery happens at the ETH query, so in for every verification query that happens in the experiment, then we actually, we can sum all the probabilities together, and we get the bound on the probability that the adversary wins. And as you can see, this is not just independent of the adversary. This is a concrete security estimate, as it clearly depends on the number of queries that the adversary can make. and at the same time on K, so on the number of computations that the verifier can make. We cannot have just a reduction to a computational problem. This depends on the adversary one actually has. And this is the necessary. This is very important when computing whether the efficiency, our new efficient verification, is actually efficient and how many times one can use it, etc. And we're going to see this exactly like right now, because once we're done with the proof, it's important. We had a look at taking this compiler, applying it to a bunch of post-quantum signatures, and see whether this would be worth the effort or not. So what you can see here is the table with a bunch of estimates, and we can see kind of signatures depending on the value of the modulus Q. And the first two rows are lattice-based signatures. The last one is rainbow, which is one of the multivariate equation based signatures. And as a disclaimer, there was an attack recently on rainbow that was published at Eurocrypt in October this year. So the parameters here are not really up to date because we had no time to update our parameters. This is just an indication on the previous parameters before this last attack. All right, so when it comes to signatures, when it comes to lattice-based signatures, sorry, one can have two kinds of modulus for fancy signatures, essentially. So homomorphic signatures and everything that can build on top of them. They already require Q to be exponential in the security parameter, which means that the estimate that we saw before, QV over Q to the K, is already 1 over 2 to the, is essentially 1 over the security parameter, which means that one can reduce C multiple times, and in particular that you already get full security if you check just one row. You don't need to check many rows. You already have the Q to the K. So if you want to have the probability that the adversary wins is 1 over the security parameter, and such probability is essentially Q to the number of queries over Q to the K. So if Q to the K, if Q is already exponential in the security parameter, then this is already 1 over 2 to the security parameter, and we're good to go. And then it's enough to take K equals 1, which is what we did here. And then we computed the concrete amortized efficiency, and we saw that already if you reuse the C twice, which is this R0 over here, then you get amortized efficiency in the sense that the cost of running 1 offline verification plus 2 online verifications is half of the cost of running normal verification. And in fact, we saw that the number of operations necessary, the online efficiency, so the number of operations that the online verification requires compared to the verification operation is 0.4%. So in this case, due to the fact that Q is so large that we already get unconditional, like we already get the same security without having to check many rows, then the online verification is really fast. When it comes to a Q that is not exponential, so for normal lattice-based signatures, and for example, here we took parameters for the Piaget with the Born lattices, which we're going to talk about in a second, because this is a very peculiar case of lattice-based signatures. It's not the one that we saw before, but parameters are quite similar for that case. So in this case, if Q is 2 to the 26, it is enough to take to check 7 rows, so 7 random linear combination of the rows of A to have security. And I have to mention that here we're assuming that the number of queries that the adversary makes is 2 to the 30. So that we want to have 2 to the 30 over 2 to the 26 to the K to be around 1 over 2 to the 128, and that's where the 7 is coming out of. And then we checked the concrete amortized efficiency, and we saw that we already started gaining in efficiency after checking 8 signatures. And the online verification only does 1.4% of the operation of the normal verification. And finally, for Rainbow, Rainbow has a very small queue. So we need a quite large number. We need to still check a quite large number of rows of A. And what we get eventually is that we have, we need to do 65 signature verifications over UC 65 times to actually have some gain in efficiency. And every online verification is more or less doing 50% of the computation of the original verification. And now you could say, well, sure, this is a great idea, good job, but you could do something even better. Like this is just, how about instead of doing this pre-computation, you just do batch verification. So you have a bunch of signatures by the same signer on different messages. Let's assume again, in this case, that B1, BK are the hash of messages. And then what you do is just instead of computing A times sigma 1 equal to V1, and then A times sigma 2 equals to V2, and all the way to K, you just compute them like sum of the signatures. They compute A times the sum of the signatures equal to the sum of the hashes. And then you also check that the partial signatures have all small norms. So this could be a very good idea. The problem is mostly that it doesn't work for all signatures, because lattice-based signatures, sometimes the A also depends on the message, and then all of a sudden this doesn't work. So this could be an idea, not the best idea. And the other issue that you have is that if you're summing too many of signatures, the vector that you're going to get, the final signature, might be very large. And then it might be easy to find that one as a solution. So it's a bit of 50, like it's not 100% unforgeable. It depends on the number of signatures you're finding. It could be possible, but it's not generic. A much more interesting direction is what one can do when one needs to verify signatures from different signers on the same message. And this is the part that might be a bit hard to understand. I apologize, but if there is someone that is interested in lattice-based signatures and what would be like a very interesting question, like this would be it. Essentially, what happens, like you can consider of doing efficient verification in specific cases. For example, when you have a board meeting of a company, at the very end there is a resolution document, and for the company to act according to the resolution document, such document has to be signed by all the members of the board. So verification, one would have to check that all the signatures of all the members of the board on the same message. And there is an efficient, like there are ways of doing it, and these schemes that allow you to do to generate a valid signature on a message through the interaction of n signers. These are called multi-signatures. And in lattices, these are really hard to build. And there is at the moment one scheme that allows you to do that, and it's based on signatures that are built from the Schnorr identification scheme. Essentially, what these are also, the signatures of this kind are also the ones that are in the process of being standardized. They are quite different from the one we saw. And what happens is that instead of producing a new vector sigma all the time, what you do in this particular signature, you show by sending a triplet of of elements down here, you show that you know one of these signatures, essentially. One of the elements, there were some, right, one of these signatures where the A and the V1 with K are in fact public, and this is just the hash of the general message. Now you can do it, so it is possible to do it. The issue with lattices is that when you send, so in the Schnorr identification scheme, when you build it from discrete log, what you have is that you first generate a commitment to a random element, then you get a random challenge, and eventually you send a vector Z, which is your signature, which has to be secret, times the challenge plus a random vector. And now what happens in classical cryptography is that all of these are random elements from a group, so Z is distributed uniformly at random. Now what happens for lattices is that this is really not true, because Z has to hide the signature, so it has to still have small norm, which means that the random vector Y cannot just be random all over the place, but it has to be a small random vector. And CS are also small. And the intuition here is that if you sign many times, so publish many of these TCZ, so many vector Z's, eventually Z starts leaking information about the secret, because all the different Z that you're going to observe will be always centered around this secret S. And that is why in lattices, you need to add another step that you can see here, and it's called rejection sampling, where you essentially adapt, reject some of the possible values of Z to make sure that the final distribution does not leak information about the secret signing key. Now, this is a very big issue when it comes to multi-signature, because if you have two signers, they need, for technical reasons, they need to start interacting at the beginning, and then so they will exchange first, like here, the first vector T, and then they will both compute C in using the same hash on the same input, so that in the end here they have the same vector C, and then both of the signer will output their own personal Z. And now if one of the two rejects, then there could be leakage at this point, as T could leak information about which randomness is not enough to hide the secret. And for this part, this is a very complex part. And if anyone is interested in that, this is really hard to do. And I have been working on this for a while. I will be more than happy to discuss about this more in details. And the topic is really more complicated if you want to do threshold signatures. So signatures where the final signature has to be generated by at least T out of the n possible signer. Sorry, this T should be a big N. Because while it seems it should be straightforward by just using Shamir's secret sharing scheme and kind of re-aggregate all the signatures together using that kind of algorithm. In practice for lattices, this doesn't work, and the reason is again linked to the fact that the norm of the signatures have to be small, because if you are combining stuff using Shamir's secret sharing, then you're going to combine things with coefficients that are not guaranteed, the Lagrange coefficients, which are not guaranteed to be small. And then you have huge issues with the norm of the thing. So at the moment, threshold signatures, there is one paper. So post-quantum threshold signatures it's not really clear how to do them. From lattices, there is one paper that builds them, but the construction is more of a, it's not really efficient at the moment. So this is also a very interesting open problem. And now to conclude, because I think I'm definitely out of time. What we talked about today was mostly a framework to analyze a signature scheme. that was augmented with a verification algorithm that is more efficient than the original verification algorithm. And we saw how to use it for in a particular case, the case of post-quantum signatures that have a verification of where there is a matrix vector multiplication check. This can be expanded to the case of flexible verification, or progressive verification, where a verifier is interrupted after a certain amount of calculation, and it can extract information. We show that it can extract meaningful information from the computation already done, even if the verification has not been conducted all the way to the end. And then there was also, in the paper, we also show a general model to combine the two. And the open questions here are many. The third one is the multi-signature tertiary signature question, which is really complicated, but the first two are also quite hard to, at the moment, they don't seem very easy. The first one is, can we apply this model to other primitives that have verification? First thing one could think of is zero knowledge proofs and any of these proofs. And then another interesting problem could be whether we could do distributed verification of signatures by using this kind of approach where many verifiers, instead of each of them running the real verification, run a very small part of the efficient verification and then compare the results. And right, and with this, I'm done. Thank you very much for listening, and thanks for inviting me. The full version of the paper is on ePrint, so in case you're looking for details, you can find it there.